In this video, we're going to continue our exploration of improper integrals, and we're going to look at something called a comparison test for integrals. The comparison test is going to help us determine if an improper integral is convergent by looking at a similar or related integral. So we're not going to find the value if it's convergent, but we will know that it is indeed convergent. So let's look at something which seems completely unrelated. Let's look at kind of the most simple comparison test I could think of. It's going to be the comparison test for low bridges. Suppose you have two trucks. One is big and one is small. Both of them have to go under a low bridge over the road where they're traveling. Well, if the big truck fits under the bridge, then you can say, well, my small truck will also fit under this bridge. If the big truck fits, the small truck must also fit. On the other hand, if you have a really small bridge and the small truck can't fit, then the big truck definitely can't fit. But there are cases where the comparison doesn't help. So for example, if the small truck can fit, then you don't know what's going to happen with the big truck. It may or may not fit. And on the other hand, if the big truck can't fit, that doesn't really give you the necessary information to be able to say whether the little truck will fit or not. So our comparison test has two meaningful parts. If the big truck fits under the bridge, the small truck must. And on the other hand, if the small truck does not fit, then there's no way the big truck's going to make it. But then we have these cases where we don't get any additional information. That's where the small truck can pass under the bridge, but we don't know about the big truck. Or we could say the big truck can't fit. Maybe the little one can, maybe not. We don't know. So let's take this as an analogy for our comparison test for integrals. Instead of a big truck and a little truck, I'm going to have two functions which are positive, so their graphs are above the x-axis, after some value a. So starting from a going to the right, their graphs have to be above the x-axis. It doesn't really matter what happens to the left of a, and it doesn't really matter what the value of a is, it just has to be some positive number. But then we have the big function f of x, the small function g of x. And the comparison test says that, okay, if the big one is convergent, then the little one has to be convergent as well. In other words, if we say convergent, meaning the analog of fitting under the bridge, then we would say, oh, the improper integral from a to infinity of the big function, if that one fits, meaning is convergent, then the small one has to be convergent as well. And then we have the other meaningful case where you could say that, look, if the small one is divergent, then the big one is also going to be divergent. So divergent means not fitting under the bridge. So if the small one doesn't fit, then the big one can't fit as well. And then we have the cases where we don't get any additional information or we can't make any other conclusion. So if the big one can't fit, meaning the big one is divergent, then you really can't say anything about the small one. It may be convergent, it may not be. We can't use the comparison test, at least with this big function, to draw any type of conclusion. And on the same token, or by this same token, if the small one is convergent, then that really doesn't give us any information about what's going to happen with the big one. It may or may not be convergent. So let's look at a few examples. Here I'm taking the integral from pi to infinity of 1 over x plus cosine squared x dx. Now finding the antiderivative would be very challenging, but we're not asked to find the value if it's convergent. We're just asked to determine if it's convergent or divergent. So there's really several things that we have to get a feel for. One is, do we think that this is going to be a convergent or divergent just based on what the integrand looks like? So in this case, when I use the comparison test, when x is large, cosine of x squared can't be any bigger than 1. So when x is large, adding 1 to 3 trillion doesn't really make a big difference in x. And so the integrand really kind of looks like 1 over x, and we know that from the p-test that if I have an integrand with 1 over x and I have an infinite integral, then that integral will be divergent. So I expect this integral to be divergent. Fine. If I expect it to be divergent, then I need to show that this integrand is larger than the integrand of a divergent integral. In other words, I'm going to consider this to be my big truck. I want to find a little truck which won't fit. Well, we're talking about 1 over x. Is it true that 1 over x plus cosine squared is greater than 1 over x? Well, no, it's not. Cosine squared x is usually a positive number, and 1 over x plus a positive number is actually smaller than 1 over x, so my inequality goes the wrong way. However, if x is bigger than pi, x plus cosine squared x is definitely smaller than twice x, right? Think about that, starting with x equals pi. If I add another pi in there, that's going to be more than cosine squared x can be, which is just 1. So now my integrand is bigger than 1 over 2x. Well, how does that impact our p-test? Well, 1 over 2x means I can factor out 1/2. What's left over is an integral where I can use the p-test, and we know it's divergent according to the p-test. So now we can say because of this inequality here, and because the small function leads to a divergent integral, then the big one has to be divergent as well by the comparison test. Now, it's important to note that when we write down these conclusions, we want to include this phrase by the comparison test. And we're going to see that in another chapter, we're going to have multiple tests. So we should start developing the habit of writing down what test we're using or justifying why we're saying it's either convergent or divergent. So here, with the small guy, I said he's divergent by the p-test, and then concluded that the bigger function, or the integral of the bigger function, is divergent by the comparison test. We can use Different strategy with this infinite integral from 1 to infinity of tanh x over e to the power of x dx, because when we use the comparison text, tanh is always between -1 and +1. It, its graph looks like an arctan graph. It has horizontal asymptotes at x equals 1 and x equals -1. And so tanh of x over e to the x when x is large really looks like 1 over e to the x. And if I replace infinity with t, and I have e to the power of -x, take the antiderivative, evaluate it, then go to step 2, let t go to infinity, I get 1 over e. So the infinite integral from 1 to infinity of e to the -x is convergent, and it converges to the value 1 over e. We would expect this to be convergent. And in this case, it's not enough for us to just say that it's convergent. We need to show that it's convergent. And since tanh of x is always less than 1, we can say that the original integrand is always less than 1 over x. And this gives us an inequality going in the correct direction. We want the tanh of x over x to be the small function. We need to have a bigger function which is convergent. So we need to have big truck which fits, then we'll know that the small truck definitely will fit. So we've shown that the infinite integral from 1 to infinity of 1 over x dx is convergent, so the big truck fits. So by the comparison test, the infinite integral from 1 to infinity of tanh of x over e to the x must also be convergent. Now here I have something which looks familiar, it looks similar to the infinite integrals we just used, but now the exponent is the quantity 1 plus x squared. And we're going to use the comparison test. It looks like e to the power of -u, and we know that if u were to equal just plain old x, we just showed that that integral is convergent. So the question is this e to the power of the quantity 1 plus x squared larger than e to the power of -x? That's not going to help us. If it's smaller, that's going to help us, because remember, we want to be smaller than the convergent integral if we want to show convergence. Now, the exponent 1 plus x squared is bigger than x for any value of x. And this function, e to the power of -u, think about the hockey stick, where the handle of the hockey stick is on the negative side or the left side of the y-axis, and it just decreases as u gets larger. So since I have a larger exponent, then I can say that e to the power of -1 plus x squared is smaller than e to the -x. So my inequality goes the right way. Since I know that this integral, the infinite integral where the integrand is e to the -x, I have a function which is smaller than e to the -x. Then by the comparison test, this infinite integral is also convergent. Here we have another infinite integral, and we have as an integrand 1 over radical 1 plus x to the power of 5. Again, calculating the antiderivative would be uh, painful, so we're going to use the comparison test. In this case, when x is bigger than 1, 1 plus x to the power of 5 is greater than x to the power of 4. Why would I say that? Well, two reasons. That'll give me a nice even power under the radical sign. If I replace 1 plus x to the power of 5 with x to the power of 4 with my comparison, and then I would get 1 over x squared, where I can use the p-test. Now, notice this, that if I can establish an inequality for the denominators, when I take the reciprocal of those, then I'm going to reverse the inequality. So that makes sense, that as the denominator gets bigger, the whole fraction will get smaller. And that tells me that my integrand is smaller than 1 over x squared. And by the p-test, we know that the infinite integral from 1 to infinity of 1 over x squared dx is convergent. So now we can apply the comparison test to our original integral and say that it is also convergent. So in the end, go back and think about the low bridge test. Think about which function represents, or which integral represents the big truck, which one represents the low truck. Make sure that your inequality is pointing in the right direction, in a meaningful direction, and then from there, you can draw your conclusion.